I try to limit the time of the lecture so that learning is more effective. So I will not spend time on reviewing the previous sessions because you have the video, you know, if you care enough, you can watch those videos. Only when something is more important, I will bring them back and re-emphasize them. Otherwise, I'll focus on the current week's content. So this week as well, the next week will be module 3, logistic regression. Logistic regression will be the ultimate model that you will learn, but we will start with the Adeline model, which is a very good starting point. Pedagogically, it's very, it sets up an intuitive framework which helps you, provides you a milestone and help you step over it and move on to logistic regression. Learning Adeline will make learning logistic regression much easier. We'll basically use the same framework. So let's get started. You may not know that there is a raise hand function in Zoom. So I'm going to ask you a few questions and raise your hand. If you answer yes, don't raise a hand. Do we have something else? Like, do we have a?
I think we have a yes or no function.
Okay, yes or no. Okay, great. So either so answer yes or no, but do not remain silent. Let's see. But I don't see. So maybe pause. So do you have? Okay, I see. No, it's in participants. You can see the option to raise a hand, right? Well, let me try to see everybody. Okay, now testing. Everybody raise your hand. All right, I see them. I mean, everybody. I only see half of the class.
I don't see.
Do you know?
Raise
Do you
your
not
hand.
know how to? Huh?
I don't see where I can select this.
So click on. I think click on participants.
Okay.
So in Zoom window under the lower section.
Yes,
when
got
you
it.
move them up, okay. Now more hands. Let me see more hands. 2 more. Three more. Yeah, 2 more. 1 more. One more. I need 1 more. 1 more hand. Oops, that was me. Sorry. Anyway, so I have all the hands. All right, clear the hands, please. I think you click yes again. It will clear the hand. Is that the way you clear your hand? Or yeah. Okay, great. Before I forget, let me make a co-host. Elaine? Okay. I don't. Okay, here. Oh, sorry. I clicked the wrong thing. I make the host, but yeah, let me. Yeah. No. I clear the option. So let me make a co-host. So window just disappeared to me. I was like, what? And it should be done. So let me ask you: Have you watched the prep video 3? Raise your hand if you did.
if you did or didn't.
If you did, yes. If you did, raise your hand. If you haven't, this is not gonna give you any penalty. Just be honest. And if you haven't, can you click no? Let me see what happens if anybody clicks no. So, okay, I do see a cross. Great, thank you. Well, if you did watch that prep video, raise your hand. Right, keep your hands up. Has everybody who has watched the video raised your hand? Yeah. Okay. Great. Now, for let's see. So keep your hands up if your answer is yes to the next questions. If your answer wasn't yes, but then your answer is yes for the next questions, also raise your hand. I mean, in Zoom, not really raise your hand. Have you watched the other videos? The homework system video for Adeline Model? Keep your hands up if you did. Let's see, if you didn't watch either of the video, if you didn't watch any of the video that's relevant to this week, put up the stop sign, the cross sign. So click no if you didn't watch any of the videos. This is just for me to be, prepared and know
How about
how much I should talk about. Mm-hmm.
How about I watch it, but I don't exactly understand the whole process?
Well, as long as you watched.
Okay.
Okay. Yeah. So the purpose of the lecture is to explain them, is to, allow questions and to help you hopefully become clearer. All right. So put your hands down. Let's get started. I will share my slides. And also, by the way, download the demo Jupyter Notebook. That's a demo for slide 3. During the lecture, I will run some demonstration codes. I will run the codes in that Jupyter Notebook. If you have them, if you have already run them, that's great. Okay, so I'm going to pace quite fast because we have quite a lot of things to talk about. If you don't stop me, if you don't have questions, I assume you know, or at least for now, you kind of understand at the basic level. Stop me if you're really confused. Okay? Right? How effective this will go depends a lot on you. Be more proactive and don't be shy. All right? So let me share my screen. Okay. So this is the focus today. Now, by the way, we will do only one breakout room today because we will have so much content to talk about. And that breakout room will give you an opportunity to kind of talk about what your confusions are and see if you share with your breakout room about the areas that you're confused, and then I will collect feedback from the groups, and I will talk about those that are more common. Okay, this week and next week is mainly the ultimate focus is logistic regression, but we start from Adeline. But Adeline is not the sort of the origin of the neural network model. There's something that precedes it that is more sort of rudimentary. but we will not talk about that too much. Adeline is more fun to talk about. Before that, there's a perceptron model that you probably hear a lot when you listen to somebody from the machine learning field talk about. Sort of the very beginning of the artificial intelligence begins with perceptron model or perceptron learning rule. And later it was improved, and the improvement resulted in the adaptive linear neuron, which is Adeline. Now, Adeline means adaptive linear neuron, and the linear part is quite important here. That introduced several things that sets up sort of the platform for further improvement in artificial intelligence. Adeline model incorporates several of the concepts that is very similar to logistic regression, and further on is the neural network. So that's why we talk a lot about this, and we use this as a important chapter module of the course. After that, we'll spend a lot of time here, Adeline model, talk about the inner workings. We'll train the model, and we'll train the model and talk about the several problems that's related to the implementation of that model. Then we'll move on to logistic regression. When we talk about that, you'll see that there isn't really any much difference between the two. They are very similar. And you can kind of see where logistic regression is highly relevant to artificial intelligence and neural network. In fact, you can, although this is sort of the original point where we start the learning, but logistic regression is considered as the stepping stone of neural network model, the more classic, fully connected, forward-feeding perceptron or multi-layer perceptron model, which is the neural network model. So, but a lot of those who use logistic regression don't even know that. That I was among them. I was part of them. More than 10 years ago, I didn't know that this has a connection with neural network model, because this model is very popular in statistics, in especially business statistics, as well as econometrics. So I was thinking that this was mostly used in statisticians and economics, but not really. There's a whole other side of the story that I wasn't aware of entirely until I started to learn machine learning. So and beginning with that, because that's more connected with the practical implementation of machine learning, we will start incorporating several other pieces, including the train test plate, and we'll conduct the hypothesis testing again to kind of reinforce the topic that was talked about last week. And we'll introduce several sort of techniques in pre-processing the train and test set, because now we have train and test. We have sort of the testing process incorporated in every project that we deal with. So we need better tools and processes to streamline the pre-processing of both sets. And then we'll move on to the critical differences between Adeline model and logistic regression. And then we'll examine overfitting and regularization, and several things that are related to them. Learning curve and validation curve. So that's the focus for today. Now, Adeline, you must have seen these charts. It's a neuron. It's a biological sort of the sketch of a neuron. And because of the popularity of neural network, you know, it will be hard for you to not see this kind of a graph. And once you are familiar with how the model works, then you will start to appreciate how, you know, how the model really is trying to imitate how the neuron works. 3 parts of the neuron correspond to 3 critical parts of an Adeline model, or I will use single layer perceptron or single layer neuron to refer to several models: Adeline, Perceptron Model, logistic regressions. They have this similar structure, and you know, even with Adeline model, it's kind of a mini-sized neural network. It's not a network per se; it's a neuron. But even with a neuron, you already have 2 layers. You have an input layer, and you have a sort of an output layer, or output layer happens here. So you already have a bunch of, you know, sort of a bunch of input nodes. I have a window there. So here, you know, you have a long list of input. This is the input layer, and you have one and only one output layer. And within that output layer, you have only one output unit. And every input unit is connected with that output unit and plus a bias term. And you have W throughout. So this structure looks already very similar to a neural network model that later you will learn in 2 weeks. So you'll kind of appreciate the similarity here. And the experiment that started, you know, almost or more than 70 years ago kind of worked. Right. So that's a little bit of a history, and, you know, I'll not talk too much about that. When you hear about perceptron learning rule, that is really the beginning of neural network literature, and it's improved in the Adeline model. Critical points here, you know, I talk about the 3 layers. I talk about the 2 layers, the input and the output, and what's happening in the output layer has the net input and activation. You'll start to see this pattern. So beginning from the hidden layer, if you have a neural network that has at least 3 layers, or if you have more hidden layer, which makes it a deeper neural network but fully connected, and as well as with more advanced deep learning, you know, convolutional and other types of deep learning models, you start to see the patterns repeating. You always have a net input and an activation. And the entire network is layers of net input, or parallel net input and activation, because each layer has several hidden units. Until you know, after activation, it's some kind of nonlinear firing of the signal, producing, in most cases, producing a continuous function that feeds the information further into the next layer, you know, until you reach the output layer and produce the classification or the result, if it's a continuous output. All right, I'll stop there. Then this process that feeds the information from left to right, from input layer all the way to output layer, it's the forward prop process. You'll hear me saying forward prop and backward prop a lot. When I explain the model, I will mostly focus on back prop because that's the process that is more complex, and that process is where the optimization happens and harder to understand. Forward prop is very intuitive. It's very intuitive, but the two are still connected because some of the steps and the results that's produced from forward prop will be reused in back prop. That's why we save some of the results from forward prop and later are used in back prop. A critical feature here about the perceptron learning rule. This is not the Adeline yet. This is the original model of perceptron neuron. A critical feature here is the nonlinear threshold function to fire the signal. So in perceptron model, it has a step function where if x is is larger than some kind of a threshold, let's say delta, then the output would be 1. If it's smaller than the threshold, the output would be 0 or -1, whatever your code is. It doesn't matter about the results. It's more of a interpretation issue. Then, then the prediction would be either 1 or 0 for a binary classification problem, like the case that we analyzed in the lecture is the credit card customer default, application. The prediction would be either that the customer defaulted or did not default, and the error is calculated based on the predicted value after the threshold function. And as much as it reflects how neurons work in animals and human thinking, it has a critical drawback in the very beginning of that model. The drawback is mostly because of that threshold step function. When it's a stepwise, when it's a step function, it produces these, sort of the kinks. It produces a function that's not smooth. It breaks the continuous function space, which leads to two drawbacks. One is that you cannot summarize the feedback effectively for the entire data set. You have to sort of calculate feedback one row after another and update the weight after calculating the forward prop and using back prop for every record. So that means more within the outer loop of training the model, which is the epochs, you have an inner loop, another loop to go through every single example one by one. With two loops, it significantly reduces efficiency and increases the time of training. So the learning rate, the speed of learning becomes slower, much slower. With our computers now, it's not a problem, but with 70 years ago, you can imagine, where mostly it's hand calculations, it becomes harder. So that's one, and also because of these non-continuous threshold to provide feedback, it creates those situations where the optimization process have reversing sort of episodes. After updating the weights for a while, for several of these sort of the training examples, the weights are improved, but suddenly the model face another misclassification case or a difficult case, and that difficult case is going to reverse the learning to something that is even worse. So the learning goes kind of like back and forth because of the way it processes the data, and the way that data or classification result is kind of quite random throughout the training set. So you have lapse or reverse weights going even worse. So you have those episodes that further slows down the learning. And that's where Adeline comes in and sort of solves those problems. It's implemented in the 60s. And if you compare the sort of the layout, the framework of the two models, the input layer are exactly the same. The net input are exactly the same. The output, where the model makes a prediction to produce the predicted label y hat. We typically use y hat to denote the predicted label. That process are also the same. The nonlinear threshold function stays. It doesn't mean that Adeline model doesn't have that. It's still a nonlinear model that fires when the signals pass a threshold. But what's critical is the feedback process. With the perceptron learning model, the feedback happens after the nonlinear threshold function, which leads to nonlinear error space. But the feedback in Adeline happens before the nonlinear, so that the net input function keeps that entire function to be still linear, and even though it adds an activation function, that activation is actually linear, which does nothing. So it didn't change anything. So the error space is kept continuous and without those kinks, and without being bothered by this. So the sort of this feedback loop is much more smooth, and the learning is improved. Also because of the elimination of the step function within learning process, it allows the program to calculate the sort of the gradient based on the full information from the data set at once. So the program can process the entire data set at once without having to do a for loop. So that's another benefit of that. So, and with these two improvements, Adeline model learns the weights much faster. So that's why we start from Adeline rather than Perceptron. Another reason we start from here, even though, I said linear activation here, this is Adeline. This is logistic regression. I didn't start from logistic regression, but started from Adeline. Even though the activation is linear, it does nothing. Why don't we simply, lose it? Well, even if it's linear, it doesn't do nothing. It kind of puts a placeholder there where you can change the activation function with a more proper function, which sigma function is a more proper function, without changing the sort of the process in the implementation. So we have a placeholder. In implementing Adeline model, we don't do anything here, or we add an additional step, which kind of may seem redundant or wasteful of time, but you can easily swap out the activation without changing, almost any part of the other implementation. So once you understand Adeline, to implement logistic regression, simply change the activation function. It doesn't even change the gradient descent process, which is more complex. We'll talk more about that very shortly. So using this reduces the complexity here, while it allows you to adapt to a logistic regression much faster later on. So that's why pedagogically it's very useful. But also, the Adeline model allows me to introduce several other concepts that are not, some of them are not relevant in the perceptron learning rule. The activation, again, PCL, PLR, perceptron learning rule doesn't have the activation function. Then the cost function was not relevant as relevant, but now we can talk about really talk about the cost function and how this function is minimized when the model learns. Backprop is more relevant, is more complete in Adeline model. The most critical part is gradient descent. I'll talk about what gradient function is. And a learning rate is relevant to both perceptron learning and Adeline, to any model, basically. But later on, I'll talk more about that. So this provides a framework and a platform to talk about many of these relevant aspects of the model. Two things I would like to sort of give a high-level introduction. Two functions are critical here, cost function and gradient function. Cost function is used to sort of measure how far off your model is currently from the ultimate perfect model. If you can imagine a perfect model where everything is predicted or classified correctly, it will have a cost value of 0. The goal of the model is try to reduce the cost function. In most of the let's see, in most of the implementation of binary target variable, where the target variable is binary, if you have 0 or 1 or true or false or yes or no outcome, like customer churn, the cost function is mostly, let me use a different pen. Hold on. The cost function is mostly sum of squared error in a binary case. Sum of squared error. So what is error here? Error in terms of Adeline, error is calculated before the threshold function, so that the feedback can be linear, or the feedback can be continuous. I see some questions. Is there questions? Yeah.
Cost function sum of square errors for any binary target or just for Adeline model?
The cost, no, it's for machine learning models for any binary target. Okay. It's not only for Adeline. Yeah. So this part is sort of the prevalent. Applies to almost all the models. Great. Soraya?
Yes, sir.
Yeah, you have a question?
Yeah, that was it.
Okay. Well, would you clear the hand?
Yeah. Sure.
Yeah, great, thanks. So what is error here? So error is the difference between the real Y, the true label, the ground truth, with your predicted value. Well, not really the predicted, but the activated value before, after the activation, but before the step function to make classifications. And I use phi, and Z is the net input. So this is the error. Error is the difference between the true label and the true value of the target and your activated value. The objective for, and I use I refers to a particular case. We'll talk more about the notations. For the ultimate goal of the model is to reduce this difference. And Y here, take values of 0 and 1. Now for value 1, the objective of the model is try to adjust the weight so that the activated value for this particular example is close to 1. Right, and for those data where the target value is 0, the activated value for that particular example needs to be close to 0. So that's the ultimate target. And when you take a square of this difference, then it doesn't matter if it's slightly larger or slower or larger or smaller than 1, as long as it's close to 1 is good. And the sum part is to sum all over the entire data set. So that is the cost function. We use J, and W is a weight. We use J to denote the cost. The cost is also referred to loss function. That's the same name. Okay, so this is something that is being minimized. The gradient descent, I will not talk about too much about how the equation of gradient descent or gradient function is derived. That's too much math, and that's too, that's more theoretical, and that's already proven many years. So we don't have to bother. If you're interested, you can look at the book. The book has the derivation process, the proof process. But how was the gradient function derived? It's based on this sum of squared function. So it's a good starting point to understand it. So that's a cost function. But then gradient function, after you derive everything, the gradient function becomes quite easy. And just to let's take a look at that. Let's see. So I have a note. And by the way, all of these are on the cheat sheet. That should be helpful. Gradient, which in Python codes, I use G, or G as short, gradient as a full name. But in linear algebra, we typically use a inverse triangle. Denote the partial derivative of the cost function with respect to W weight. The gradient becomes quite easy. The gradient is calculated as minus the transposed X, or sometimes it's input matrix, or the activated matrix from the previous layer. Here we only have 2 layers. So for the output, for the activation, it's the previous layer is the input, so it's X. A matrix multiply the error. So now we have the error from before. So, and this part is the error. Gradient becomes quite easy to calculate after deriving the math. And here, what is error? Error is true label minus the activated value of Z, and activation is simply a function. It doesn't introduce any uncertainty. What really matters is what's inside Z. And what comes in Z is mainly the input data and the weights W. So this function depends on W. With changing the W, with the W being changed and replaced after each loop, each for loop, the models kind of learn the patterns inside the data and try to reduce the costs. And you know, this gradient, this is the gradient. Gradient also depends on both X and W. All right. So that's two things. We'll talk more about it in the process to better understand that. I mentioned the cheat sheet. I hope that these cheat sheets will be helpful. For every model that I talk about, there are 3 cheat sheets. One is the implementation timeline, what happens first and next, and what are they, and what more specific steps are inside with additional information. And when the for loop exits and enters, and what happens before and after. That's one. Another version of the same timeline involves the notes of 3 things and color-coded. You have blue, which describes the formula in terms of particular training example. Maybe more familiar with these and easier to understand. But in implementing Python, we're not following these formula exactly because we want efficiency. So we translate that into matrix notation, which is closer to the Python codes, even though they are less intuitive and more difficult to understand. But I'll talk about these. The more important part in understanding the matrix notation is to understand the shapes of the dimensions of each of the components. Once you understand those, it's much easier to see how they are linked and to understand what is being calculated. Once you understand the matrix notation, then translating that to Python code is very easy. So, so gray is dark gray is the Python implementation. The third cheat sheet would be like this: the process illustration of steps inside the for loop. What's included in the for loop is the main components of the model. The weights are updated by the calculations happening inside the for loop. What goes before the for loop includes preparing Y and X and Y data. Later on, we will have train and test. For now, we only have train to make it simpler. We have initialization process, init, to stands for initialization, including starting to draw the weights, the old weights, which will be updated. And we also have delta weights. These two have the same dimension. We need these, but we don't need to initialize or have a placeholder for the W new, because W new will be directly calculated based on W old and delta W. However, we need these to draw the numbers to start the forward prop. At least we need something to start the forward prop, right? The initial step. We also need these because we are referring to different parts of that vector, this is the vector for now. We are referring to different parts of that vector for calculating the weight update. So we need the placeholder for now. To start, the values of these will all be 0, but they will be replaced in the very beginning, in the first loop. We also need to initialize ADA, which is learning rate. We need epoches, and in Adeline, I have a spelling error, but I will keep using that spelling error. And we have a random state to control the random join process, random number generating process, so that you will have the same results as I do. So that's the preparation. That's only just one step. Once the model trains, you don't have to do that again. The loop will repeat for many times though, and that's where most of the calculation happens. That's why it's important. Three main step here. The third step is major. The first step is net input. We use Z is used in matrix notation as well as the Python code because it's easier to remember. We have the net input. So that's more of the first, before the first dash line. The second part is the activation, by which we also calculate the error, because recall that error, previously I said error is difference between the Y label and the activated value. So after calculating the activation, you can calculate error. That's a second step. Once you have the error, now you can begin the backprop process. So this is more of a forward prop. Up until activation, it's forward prop. Beginning with error is kind of a backprop process. And in the third step, it's where optimization happens. Has several steps. You calculate the gradient, you calculate the weight update, and then use the weight update and the old weights to create the new weights, and then replace the old weights. And then you're ready to begin the next loop. You know, it's a loop process. So here I'm going to talk about each of these three things, and three little things in the third component, and just to go through one loop to kind of understand what happens. Good? Any questions for now? So let's keep going. These two videos talk about the sort of has some additional tricks to kind of talk about, including Jupyter Notebook tips. But I'm sure that you now are much more familiar with Jupyter Notebook than beginning, so you can kind of fast forward those. But after today's lecture, if you haven't watched these, or even if you have watched it once but were kind of confusing, what was it doing? After today's lecture, you look at that again, you watch them. I believe it will become much more intuitive and makes more sense to you. Key things to keep in mind are the three things that I talk about, basically: the net input, right? The activation and error. And the third step is a gradient descent, which calculates weight update, and then finally update the weight. Updating the weight is the main purpose of doing the for loop, because the cost simply depends on the weights. By optimizing the weights and by repeatedly improving the weights, the cost is getting reduced. That's the essential mechanism of the model learning. All right, I'll talk about these steps using this case, and you're very familiar with this. Credit card company, a bank, basically, and credit card customers recorded the activities of these customers as well as the demographics, a few demographic information. Sort of panel data set where for each customer, it records several months of activity. And we have a target, which is whether or not the customer default in the current month, right? Different types of variables color-coded, you can look at them. It's quite intuitive. to understand by this point. For now, for the first implementation, we'll only focus on those continuous variables, those in gray. We will not pay attention to these for now. So initialization, what does it do? What does it need? For the next few slides, you'll see this portion remains the same. These are simply background information to refer to, so that I don't have to write them in multiple slides. I can refer to them as a reference. So initialization has several pieces of things. Let's see. So notations, N and M. I will keep using these notations throughout the course so that we don't have to kind of adapt to new things. Let me use black. So N, I use N to refer to the number of training examples. As you can see here, the training set has N examples, N rows. M is the number of sort of the real input variables that you have. M may be different from the number of columns in your original data set when you read in the data from CSV file. Why? There may be ID columns that may not be used as the input, right? There may be other information that's not appropriate to be used in training the model. Those kind of features may not be useful or maybe too hard to use, like free texts. You know, notes about a customer may not be effectively incorporated in the model. Only the quantitative information can be incorporated. But also there are categorical variables that needs to be converted to flag variables before you can incorporate them in the model. So the number of variables will increase because of categorical variables in the original data set. You know, ID will reduce the number of variables because ID will not be used. So this M may not be the same as the data set, original data set. But after pre-processing X, you know, after pre-processing X, we have X pre-processed. That would be the number of columns in that data set or data frame will be the same as M. And because of this M, it will be the same as the weight vector. Here for Adeline, it's the weight vector. Weight is a vector here. That's a vector. All of these are, this is a scalar. This is vector, right? All of these are vector. The real information from the data for each training example includes the X variables from X1 to Xm, right? So there are M real input variables here. But the weight vector has M+1 elements because it has an additional bias term. This bias term is similar to the intercept term in linear regression, but it kind of creates a sort of a difficulty in implementing the model, because the way you calculate the weight update is different for the bias as versus for the other. So you have a two-step process when you calculate the weight update. We'll talk more about that. Need to initialize eta. Eta should be a smaller number between 0 and 0.1, and eta actually, you know, you will not think that eta will have a critical role in real implementation, but that's actually the factor that throws many people off. You know, you may think that after 10 hours of work to put together an Adeline model, and finally I can train. The training goes off track and kind of deviates from what you expect. And the whole reason behind that is because eta is not appropriately chosen. And you kind of get disappointed, but that kind of, that will teach you a lesson that every part of the model is important, not only the for loop, the fancy equations, but as simple as a learning rate will decide whether or not the learning is successful. All right, so these are mostly epoches. For the first loop, epoch is not relevant. When we put the for loop together, that's when epoch will be relevant. All right, so that's the initialization. We'll prepare the x and y data. Y is a vector. It has n true labels for the training set. Now here begins the first net input. And this is when I refer to, this, the process is within the for loop. Net input, activation and error, and then backprop. You may also refer to the implementation timeline. I will begin talking about these three things, right? The first step is net input. It's quite easy, quite intuitive. In black, yeah. So how is it calculated? If you imagine a particular training example, so the first customer in the training data, what do we have for that? For this particular customer, we have m number of variables. And we have generated randomly a vector of m plus 1 weights. So we will basically use these two vectors to calculate the net input for I. Hold on. I think I need to speed up because I really want to finish at 7:30. So net input is multiply x and w weight of the corresponding number, and the total number of x is m all the way, and I use j to refer to a particular example of the variable. So j indexes the number of variable and up to m. And very critical, don't forget the bias term here, which does not have an x to correspond to it, but you can imagine it as 1 as the data point, because this is very similar to the intercept term of regression. So put these all together, you have a sum of multiplied terms. It indexes j, goes from j to m. Remember, this is only one case, one training example, right? So it's every weight times every input variable for this particular training example, it's I. And you have I superscript for every term here and nothing here. Or you can say it's 1 regardless, and plus the weight 0. Don't forget that, right? So that's the net input. If you have 100 variables here, doing Python to implement this equation will be tedious, will be very hard. You may use a for loop to go through, so then another for loop, and that is kind of wasteful of time for computation. So you have a better tool is to use the matrix. We use capital Z to denote the vector, maybe. Z is a vector, so we use lowercase. It's a vector, and Z in matrix term is very easy to calculate. Switch between X and W because X is the matrix and X, the number of rows correspond between X and Z. I'll talk more about that. And this is matrix multiplying the W weight, but only those M elements for here, right? And plus the scalar W0. Anyway, so that's the matrix, and this corresponds to Python codes very closely. But I like to point out that W0 and W are all of them are inside this weight. So take a look at the weight, the old weight vector. If we imagine it's a column vector, then the first one is bias, beginning with the second. There are M elements of weight. So this part refers to the part of the weight vector that begins with the index 1, and weight and the bias corresponds only to the first element of the weight vector. So that's hold on. Okay, it's here. So let me see. Where's the chat? Let's see the chat. Anyway. All right, so that's Z, and it's helpful to understand the dimension. Z is a vector, column vector, has n rows, one column. X has n rows in M column, as indicated here. And what is W? W is a vector that has M, and this part of the W has M elements and one column. You multiply these two, it becomes a column vector of n by 1 plus a scalar, So a scalar is added to every row. The end result is n by 1 column, which is the same as Z. So by the end of the day of a net input, you have a column vector. And let's run the Python code. We have a specific step for this. Let's see. So I've already run these, so I won't run them exactly. But you can kind of see the similarity. Z is calculated by multiplying the matrix and the vector. We use a dot multiplication function of NumPy, right? So dot multiply X, and the part of the weight vector that begins with index 1 that corresponds to M elements, and plus the first element of the weight vector, which is scalar, you get this. You can do that as one way, but you have an alternative way, because NumPy array has the dot method already. So you can do dot x dot weight, or weight ode, beginning with the first index. That does the same thing as the code here. That's the same thing. And this way is even shorter, saves more space, and does the same thing. Make sure you can get the same results for the first 9 values of this vector. So that's the net input. It's not very complicated, right? Even the math may look like complicated, but it's not really very complicated. With Python code, it looks just so simple, kind of a delusion. All right. Once you have net input, you can calculate the activation. And because Adeline model has linear activation, you can do nothing. Or you create a placeholder, create a header, and times the z net input with 1, which doesn't change anything. And use the for now I use z act, which is activation function. You can do this as well. So it doesn't do anything, or you multiply by 1, it creates a copy of that values and make it a new variable. I use z act to make it clear. Later on, I use a as activation. When we have more layers, neural networks, we have more layers. We need to simplify the notation. So a means activation by then. For now, it's z act just to show the difference. Now, when you have the activation, you can calculate error, right? I think it's very intuitive. I didn't even have to talk too much. Once you understand the net input, then the error is the difference between true label in Y and the activated value of Z. So you simply take a difference. Notice the order. The order is very important here. You need to subtract activated value from the true labels, not the other way around. If you switch the order without adjusting the other parts, your entire model will go the other direction. It's kind of giving you the wrong input and throw the model off the track very significantly. After calculating the error, take a look at the error. The dimension of the error will be the same as the activated value, right? Error E refers to the error in matrix notation. Error is the difference between Y and the activated value, right? So the dimension will remain the same. Dimension of Y is n by 1. Dimension of the activated value is n by 1, and E is n by 1. In NumPy, this is sort of the one-dimensional array, which only has a number for one dimension. The other dimension is empty. And you have the error. Once you have the error, you can start the third component, which is the back propagation. You already started back propagation, but you can start the gradient function. Now I already talked about the gradient function. The calculation of that is with respect to W, based on the sum of squared error, cost function. The gradient is calculated by minus input data transposed times the error that you just calculated from above, from the previous slides. And this gradient applies to both the weights that are the M weights that are associated with the input variable, as well as the bias term. But for the bias term, X will reduce to a 1 vector, right? So let's take a look here for the gradient. Calculation is not terrible. In Python, you use the transpose, that T transpose, to transpose X, and because it's matrix multiplication, you use dot function or dot method. Don't forget the minus term. It's very important here. You miss that, the model is very hard to debug, and you kind of are stuck. So when you debug the code, these minus terms are the first step that you should debug. Now, before I talk about weight update, let me talk a little about the gradient. So why do we calculate gradient? You may know what it means, then you can skip this part. But if you don't really understand what gradient is, let me talk about that. Gradient function with a lot of weights are difficult to illustrate. So for now, I'll assume that we have a very simple training set. We have one variable. So when I say xj is referred to x, we only have x or x1. Let me use blood. Okay. So with only one variable, I can draw a graph, right? And with only one variable, let's plot the cost. And with one x, we have one w for the x term, which is w1, but we also have w0, which is which doesn't affect too much of the we'll focus on w1 for the optimization. For only one variable, what is the cost? The cost will be sum of squares. Again, it's a sum of squared errors, and the error now is with Adeline, it's linear activation. So the activated part is the net input. And what's the net input? Is the combination between W1, X1 and the weight. And because the weight is sort of a scalar, it doesn't depend on X. We'll figure that out after we figure out the W1. So by the end of the day, this equation is a function of W1, and it looks like it's this kind of function. So that's the cost. And by random initialization, we have, let's say we have a W ode or W1. Yeah, W1 ode is here. It's not as perfect, but it's good enough, which produces a model that produces an objective function, sum of the squared error as here. But see that our objective is here. We need the model to update the weight so that the weight goes from here to that, and the difference is W. It is delta W, right? So we need to have some kind of mechanism to find out how to move from here to that. And that's when the gradient comes in place. The gradient is the slope of the quadratic function of the cost. So for this gradient, here now, at this point, let's say, it's definitely greater than 0. We can say it's probably 2. That's a gradient. Gradient is 2, it's larger than 0. We need to have a delta W, which is smaller than 0, right? Because we need to update W ode to W new, and W ode is larger, so we need this term to be smaller than 0 to move leftward. However, the gradient is greater than 0, so you can't follow the direction of the gradient. You will go farther away. You have to reverse the sign and go toward the downslope. You have to go down the gradient. That's why we say gradient descent. That's a gradient descent. By going opposite to the direction of the gradient, we're descending, we're trying to improve the model and find the minimum of the cost. So that's, you know, so that's the sort of intuition behind the gradient descent. And here, this opposite direction between gradient and the delta is reflected in the negative sign in calculating the weight update, which is the next step. Once we have the gradient, the weight update is again quite intuitive. For those W that begins with index 1. For this part, the calculation is very straightforward. You have the negative sign. This negative sign is the reversing the gradient direction that I was talking about. This negative sign is very critical to make sure the weight update is goes in the right direction. It's minus eta. Eta is the learning rate. It affects the real implementation, the success of real implementation of the model. You will see the effect when we do the demo. It's minus the eta and then the gradient. So it's very simple here. Once you have the gradient, you have the initial value of eta. You calculate the weight update for the m. This has m number of elements like this, right? Or delta weight beginning with index 1, it has m elements. So that's the first step of weight update. The second step of weight update is to take care of the bias term. How to update the bias term? It's again applying that function, but now the g, remember what g is? G is minus x transpose times error. But here, the bias term does not have a real x. It only has a vector of 1. So it reduces to something like this, sort of like a vector of 1 multiplied by the error. This is what goes behind the scene for the weight update of the bias. And, you know, to calculate this, it's even simpler to use the element-wise function of NumPy. What you're doing is trying to sum all the e inside this, right? But don't forget to have the negative sign here. It has a negative sign. So both negative sign will cancel out when you implement Python. It becomes eta is the NumPy variable, is the Python variable for learning rate. And you can use two ways to do it. You can use NumPy sum error. You calculate from before, or another way is alternatively is to use error.sum. It's a vector, so anyway, it will produce a scalar. By the end of the day, this is just a scalar to replace the content in the delta weight matrix vector. So I was just talking about these, how to get the weight update by doing 2 steps, right? And print the entire delta weight, because we only have 15 weights. So the entire vector is not too long. You can take a look at the full information in the weights. After that, updating the weight is very simple. You plus the old weight and the delta weight, it becomes the new weight. I printed out the old weight before I replaced the old weight, and then also printed the new weight. You can see how the weights are updated from, you know, this small, very close to zero, the values were very close to zero, they are randomly drawn to become more than 1. In some cases to more than close to 3. So just by one update, the weights are changed for quite a lot. And something interesting to note is that the gradient, in one of the steps, we have the gradient. Observe how the gradient is so big. It's hundreds and hundreds. Because the gradient is big, you know, because this is a complex function, in some of the spaces, the gradient terrain is quite steep. You have a large gradient. If we also have a large learning rate, the multiplication between the learning rate and the gradient will produce something, the update to be too large, will overshoot the target. That's why we need to have the learning rate to be very small. Especially in Adeline model, because Adeline didn't have the nonlinear activation function. It's linear activation. So it it allows the extreme values to be to enter directly into the gradient function. So that's why the gradient can be very large. You will need a learning rate that's very small. When we do implementation, you'll see the effect. Right after the weight update, the for loop finished one iteration. Now let's put the for loop together to see the big picture. It's the 5 or 6 code cells. Put them together. You need to reinitialize to make sure you begin with the same initial values, right? And once you put the for loop together, it's quite elegant. It's not very long, but it consists of the 3 major parts: net input, activation and error, and then the optimization. And then by the end, we will calculate the cost, right? And within the loop, so that we can track the for loop, track the error, track the cost function value after each loop to see the learning curve. Cost, as I said, is a sum squared error, right? So because you calculated error earlier, it's quite convenient to calculate the cost. Once you have error, your objective is to take a square of every element of error and then to sum all of them together. Well, of course, in NumPy, in Python, the code for taking the square is to double as the rod 2. Another way is to use matrix notation, is because error is a vector. You can do error dot error. Same thing, produce exactly the same result. And here I'm using the dot notation. Whether or not you divide it by 2 is trivial. To be faithful with the gradient function, we divide it by 2 because they started from the same cost function. So with the learning rate, here is the effect of learning rate. Now I use learning rate of 0.01. You would think this is small enough, right? But after training 10 epochs, observe the cost. The cost can be minimal 0, but it can be infinitely large. For 10 epochs, it goes from 9 to, I don't know this number. This is too large. This has 31 digits. It explodes. That means something is not going right, but the mechanism is right. The steps are right. The only thing that goes wrong is the learning rate. It's too big. Every time it updates, it overshoots over and over and over. When you overshoot, the problem is that, you know, for the simpler case, your original weight is here. When you overshoot, it goes there. The gradient becomes steeper. With a large learning rate, it overshoots again. It becomes even steeper, the slope, it overshoots again. So over time, it's gradient ascend, not gradient descend, right? So we need to have a better learning rate. So now lesson learned, we choose something much smaller. This is 100 times smaller, right? When you choose ADA, first decide which direction you should take. Is the learning too slow, or is the learning become worse? If the learning is becoming worse, your ADA is too large. Reduce by 10 and try again. My ADA was 0.01. Then I tried 0.001. Didn't work really. And then I tried 0.0001. It started to work with the cost value reducing, but reducing too slow. So I multiplied by 2, so 0.0002. It works quite well, right? With the new learning rate, the implementation didn't change. Simply trained for 10 epochs. I made a graph. You can see how beautiful the curve is. You know, the cost value reduced sharply in the first few epochs, then it slows down. That's what happens with learning. You know, there are less room for improvement, so the learning rate slows down, but still it's learning. So you can train it for more. The last step, let's see. Okay, it's quite on track. Great. Now, with so this is a recap of the steps. We have implemented a complete loop. We put the loop together with reinitialization, right? We trained the model for 10 epochs. The learning happened with an appropriate learning rate. It learned by showing this learning curve. It has more room for improvement. And we remember we also saved the costs. That's how we can plot the learning curve. And by the end, we have a model that's trained for 10 epochs. Now let's make some predictions. We have done this. We have improved the learning rate. Now let's make predictions. With the model that you have right now, after being trained 10 times, how does it do on the training set? What does that mean? Okay. So to calculate performance, for binary classification, we typically calculate accuracy, right? So the accuracy is calculated by the percentage of correct classification. So we need to make classification first. Recall that the activation is linear. Whatever your z-act is, then you project, whatever your z is, your z-act is projected to this diagonal line. And based on that, we use a threshold function to make classifications. We use 0.05 as threshold function, as threshold value, because it lies in the center between 0 and 1. 0 and 1 are the target labels that we use to encode the credit card default. We use the center point because the activation is a linear line. The center point would produce the center space of the activated value. So that's how we choose the threshold function. When you read the book, it may use a different threshold value because of labeling. they label it as -1 and +1. That's why they use the threshold value of 0. So this is accustomed to the target value, the target labels. Right. Hold on. And in Python, we basically use the Z-act. So we do another for loop because now we have updated the weight. The weight is updated. We use the weight to perform one more forward loop that goes through net input and activation. So basically 2 steps. And then after that, we use the act and compare with the threshold value of 0.5. Whenever this value is greater than that threshold, right, its classification is 1, otherwise it's 0. So here is what the code implements. A forward loop has 2 steps. We don't have to calculate error here because we're not doing the back prop. We're only doing the forward prop, right? And then use the threshold comparison function. And after that, we have a Boolean vector. You need to convert that into the integer type or float type, whatever. This doesn't make too much of a difference. Then you have the predicted labels. Once you have predicted labels, you can compare with the true ground truth and calculate the number of correct points or calculate the accuracy. I'm using a function from sklearn here. The model performed well. The accuracy is 96.4%, which is very good. Even after only 10 epochs, it learned well. It's kind of very amazing here. So that concludes the Adeline model. The caveat here is that even with 96% accuracy, it is only using the training set only. Could this be overfitting? You wonder? Even only after 10 epochs? It's possible. Because what's learned from the training set may not be the whole story. There may be noise. The model may be too custom to the training set. The learning process is efficient. In only 10 epochs, it increases. Originally, the prediction rate was perhaps 78%. It improved to 96% in 10 epochs. So the learning is quick. But could it be overfitting with only the training set? Maybe. We will need to examine that. So that concludes the Adeline model. I think it's time for you to talk now. Let me stop the share for now. And yeah, so let's do a Zoom breakout. For those of you who prepared for this class and sort of took a look at the slides and the book as well as the videos, I hope what I talked about just now helps a little bit of understanding. But I'm sure you have questions. So in groups, talk about what your confusion is. Talk about what part may need to make more sense to you, and see if you can find a quick answer from your teammates. Otherwise, not teammates, breakout roommates. If you can find a quick answer, that is great. But if your group share the same confusion, then surface it up, and I'll talk about that to the whole class. Right? So let me put into groups, breakout rooms. Oh, guys, hey, you're friends. Okay, you're here. We want to talk about?
I think I might have to. Your lecture right now is like really technical as well. You know, sometimes it's like hard to like follow along.
Okay, so which part? Let's revisit those.
Like when you were starting with logistic regression, we started with Adeline Model, right? And
Yeah.
I had a lot of energy in the beginning.
Yeah.
As the lecture progressed, slowly started going down. And
yeah, but you prepared. So which part didn't add up?
I have to like go over the videos again to understand what I don't understand, you know.
Well, you know, the implementation process will require you to sort of follow, you know, what's happening. Yeah. So maybe the question is, why do we need to do the net input? Why do we need to use the activation? And the activation is linear. It doesn't do anything. Why do we need that? And why do we calculate the error like that? Maybe the question is like that.
I don't have any questions like that at the moment. Like maybe afterwards, you know.
Okay, so I'll give you more time. Of course, you can watch the recordings, you know, but don't be afraid of that, you know, technical parts and the math. And Python makes it really easy once you have the matrix notation.
Mm-hmm.
Right. So any other questions?
No, like I had the same problem. Like I haven't studied Python a lot, so it's a bit difficult to follow up with all the technical wordings and all the gibberish that happens in the class. So I had the same problem as Efrat, like all the technical words.
What are the technical words?
Like the regression models, Adeline models, all the coding and everything. Like
yeah, so Adeline model is just a name. You don't have to really, you know, it doesn't mean it. You know, it's a famous model. It's a good platform to learn neural network. It's a good starting point. That's it. You know, it doesn't. When you say the LLM model, it doesn't speak magic. What really speaks magic is to understand how the model learns. You know, what goes inside the for loop. You know, why does the for loop allow the model to learn? That's really the you know, the backbone of what's going on. It's okay to not, you know, following up completely. You can watch the video. You can pause anytime. Nobody is pressuring you, right? And follow along at your own speed, but you still need to follow along. There's no skipping. Skipping won't work. Skipping will make you more confused later on, right? Because imagine that you're in the exam. The exam will ask you to implement the for loop. Will ask you to write the code. You know, imagine that you're inside that. How you need to kind of understand the roadmap, right? And I think it doesn't require any technical background. You all have learned linear algebra, and it's not like you have to derive the formula. The formula is given to you, but simply implement. You know, seeing the connection between the matrix notation and the formula that takes the perspective of training example may be hard, but once you have the matrix notation, you can skip the you know, derivation part. You can take the matrix notation and put it into Python codes, and that's really what helps here.
I
Right.
agree. I agree. I mean, like the only reason why I feel like I'm skipping something over here because I haven't taken the previous Python course, the advanced programming one. So I know the algorithm, but it becomes a bit challenging to apply the logic. For example, on the previous one, the 12th and 13th one, the most difficult one for me, because I'm not that used to Python. So like I had to practice a lot, and because of that I'm lagging a bit.
Well, that's not necessary. So I'm not testing your Python knowledge.
Mhm.
I'm not testing your Python knowledge. I think as long as you see that here is a matrix notation, here is a Python code to implement that, and the two map with each other quite well. This is it. This is it. Even for homework for the exam, you need to understand Python at this level. I'm not asking you to do crazy things with Python with the data. It's not the purpose of this course. There's no need. I think there's no need to be afraid of Python, and Python shouldn't be your roadblock. It doesn't have to be. An error in Python when you try to implement, the materials from this course in homework, when you get an error, that may be a roadblock, and then that's where I can help you, very quickly. Other than that, if you didn't even have an error, there's no need to really being afraid, right? Embrace the world. That's, hopefully gives you a nudge. Arjun, how are you doing? Arjun is
Yes,
okay. How are you doing?
doing good, Professor. The same is the problem with me. I haven't really watched the video before, so that's why I'm not following it.
Okay, so homework 2 is due next week, so you need to hurry up. No, so
Yes.
I think the time is over for the breakout room. I kind of get a sense. Thanks for your feedback. Let me go back to the room.
Okay.
Okay. So we're back to the full room, and let's see. Now, so quite a few have left. Anyway, so I get a sense that they haven't returned from. All right, we have all. So I was in one of the breakout room. I get the sense that if you didn't preview the materials, or if you didn't watch the video, or even if you watched the video but didn't, let's see, if you didn't try to think about the process, then it's kind of difficult to follow, particularly with the let's see, with the Python. A few of you didn't take Python courses before, but a few of you have done. For those who have learned Python, let me ask you, Korean, Elaine, Sahithya, several of you have learned Python. What do you think about following along what I talked about for Adeline Model? Given that you may have not watched the video, or you may have watched the video, let me know if you watched or didn't watch, and let me know how well did you follow what I talked about? Do they make sense at least?
So it made sense, but it was a lot of like math concepts and just a lot of like, holy crap, what's going on? So I'm definitely gonna need to go and
that's a frustration. I sort of foresee that. I think that there's a threshold over which you start to kind of feel ease or comfortable. That's when I think that's when you have at least done the problems once and got the result. I think that will give you the kind of the positive pump. Before that, it's kind of a mountain, and I don't know how. I don't know when I can get over it. At this point, don't be bothered about trying to understand. Oh, you can't. It's just, it's decades of research behind. How can you expect to understand everything
Agree.
in 1 or 2 days? That's not the purpose. The purpose is for me to hold your hand, go through this. Once you go through this, you start to see, start to pick up things, and you have your own interpretation. And that's really important. That comes after. It comes after.
Yeah, I think that with more hands-on and more practical practice, I guess, it'll be a lot more understandable.
Yeah, and several things. The terms, there are many symbols here. There are different variables. It's hard to pick a point and start. That's right. So I think homework 2 becomes very valuable. After homework 2, you have taken a lot of the videos inside, you have taken a lot of the materials, you have done the problem. If you've done it, if you did it well, if you get the results, then hopefully you start to feel better and be more willing to take in. Then every time you revisit, you will think of new things. You'll start to realize things that you didn't you're reluctant to think about. But the initial learning curve is kind of very steep. Anyway, hopefully you'll have fun. I think it's better for me to stop here and give you a week to slowly take it in, use the videos. I think for understanding the process, for understanding the implementation, it's better to use those videos. For a little bit more explanation or intuitions, you can replay this video. Some part of this lecture talks about the intuitions. If you have more questions, more specific, better. It's better if you ask more specific questions. If you have an error, email me, paste the error as well as the codes that produce the error. I think I can help with 99% of the bugs, but I can't help the other 1% of the bugs. Sometimes, you have seen this. Sometimes Python, some of the package is updated. It has bugs in it. It takes probably 2 days for those bugs to be resolved. But in those 2 days, don't drive your own self crazy, because no one is able to solve that in these 2 days. And afterwards, it gets solved. So that's it. Well, it's already longer than I thought. I was planning for an hour. But with an hour, I think I'll be better at making you sleep than really talking about things. Any other questions? We can use the time now. If there's I think for now, if you focus on the matrix notation and the Python codes to see if you can map those together. In the cheat sheet, it's a black handwritten notes. The blue part are really for your reference. You don't have to really pay. If you just, I don't want to touch it. Feel free. Focus on the Python part. See if you can map them. It's mostly very straightforward. Type it into your Jupyter notebook, or simply use the demonstration, the demo Jupyter notebook. Simply, examine it and run it. It will give you the positive results. Once you go and play around. But if I do this, oh, I got an error. Why? Play around. It will help you a lot. So, at this point, focus on the questions in the homework. And all of these demos, they are directly related to the homework. Nothing is wasted. So you are not doing extra work for nothing. You are preparing for the homework. Question? Yeah, Melanie?
How many books you should... How do you know how many books you should use?
ePoach?
Yes, ePoach.
ePoach. Do you know what ePoach is? Do Do you know what a poach is?
It's like one cycle.
Yeah, in machine learning it is, but why? This word has a real meaning. Korean knows. A poach. A poach. I mean, not e-poach. E-poach. I mean, get rid of the e. It's poach. I think poach means a bag. The poach that kangaroo has, right?
Okay,
Yeah.
okay, yeah.
So it's a bag of things, and every e-poach is one process, one loop process.
One loop.
A loop
Okay.
contains these sort of very important processes. So right, so epoch. How many epochs do you need? As you see here from this example, the data has 1,000 rows. It's not small. From any statistical analysis point of view, it's not a small data set. It has 17 or 19 columns in the training set after being pre-processed. For this size of the data set, 10 epochs increases the error, the accuracy from 78% or 79% to 96%. So you don't need a lot. We are using the gradient descent based on the entire data set. It's even slower. Later, you will learn gradient, sort of the mini batch. It is more of a stochastic gradient descent. It increases the learning speed. So by then, you even need fewer epochs. But again, this data set is sort of a toy data set. So the data set is somehow sort of provides a good experience for learning. For real data set, for real life data set, particularly in business, and for those tough problems, those data sets will be noisier, has all noises in it. Typically 10 epochs are not enough. You probably need at least 100 to get to somewhere that's close. But later we'll talk about regularization. Without regularization, when you increase epochs, the model will really get overfitted to the data. With regularization, you can train a model for 10,000 epochs, which is more than anything you will need in training neural networks. With 10,000 epochs, the model remains stable with good regularization. So really, the epochs, in the end, it won't matter, right?
Okay.
I would say 100 or 200 or 500 will be a comfortable region for typical problems. Yeah. Any other questions? In terms of Python, I can really help you now. Also,
even the 1%.
huh?
Even the 1%. You say you can really help us now?
No. 90. Let's remain in the 99%. So also, if you think you will need a lot of help, which I hope it won't be true, but if you think you need a lot of help, it will be convenient if you install the Chrome remote desktop. Chrome remote desktop will allow remote access, which will come in handy when you have an error and I try to diagnose. Instead of giving you orders to do things, I can control your computer. Will become easier for me to diagnose and save both our time. I can put instructions in Blackboard on how to install the Chrome remote desktop, and you can grant me access whenever we need to diagnose. Anything else, or we can dismiss the class. Can't wait. Yeah. All right, so let's call it a day. Let me know if you need help or stay for questions. See you. Have a good night.
Bye. Thank you.
Bye.
Thank you.
Mm-hmm.
Hello, sir. Professor, I have a doubt about something.
Yeah.
After going through the process, I've been thinking. Imagine we have a data which weighs around terabytes, and we just got billions of rows. So in that case, going through a for loop, going through all the model, looking at the cost function, changing the ETA value, doing it again, changing the ETA value, doing it again, changing the ETA value. Don't you think it's computationally complex? Is there any way to fix this? I mean,
so let me try to understand the question. You mean the data is super large?
Yes, sir.
And data is super large, going through the for loop.
Yes.
What's the problem?
We go through the for loop. We look at the cost. We look at the cost values.
Yeah.
And we are not satisfied. And then we change the ETA, and we have to go through the entire process again.
Okay, I see. I see.
This
So
is complex
let me give you a short answer. For that size of a data set, you would typically not use Adeline.
Yeah.
Right. So Adeline is it's like a I don't know, kindergarten.
Yeah, true.
Learning, machine learning. So I mean, artificial neural network. With that big of a data set, you will use a lot of improvements in terms of model. So with improvements, you won't need. I mean, the learning rate will start to become easier to choose. So that's one thing. And when you have great stochastic gradient descent, the training process is easier to converge. That's one thing. And also, so another good trick is that instead of using the entire data set that you have terabytes, you take a random sample to start to feel about where is the comfortable region of those meta sort of the hyperparameter. So take a small sample and try out a few things. Find a comfortable region for those hyperparameters. Then start to be more serious with the entire data set. So that should be the mentality, the best practice in industry. Yeah.
Does that work? Because the terabyte of data we're having is a sample. Again, we're getting a subset of the sample.
Yeah.
So is it okay?
Yeah.
Is it a good option?
Of course. I mean that's something you have to do. You can't. Terabytes of data will require how many memory? We don't have even those memories, right? So with real implementation, with terabyte data, we never do the for loop with the entire data set coming into the for loop. We always have mini batches. We call them mini batches. With mini batches, it reduces the demand for memory and increases the efficiency. That's kind of a no-brainer choice.
There's another question, sir. You said cost is sum of square errors for a binary target variable. Yeah, but in our case, while performing the logistic regression, our cost function was quite different. Why is that?
For which model?
For logistic regression.
For logistic regression, so here's why. Sum of squared error, sum of squared error is actually used to derive the gradient function for logistic regression. It's kind of hard to see that because the math is behind. So the gradient function doesn't change too much when we switch from Adeline to logistic regression. The reason is because the cost function is the same. The sum is squared. It gives us very elegant gradient descent process we can reuse. But then when we calculate the cost per se, we change it to something else. And here's why. We change it to something called binary entropy, or the y and the y and 1 minus y. That's called cross entropy cost. And the reason for doing that is because one benefit of using logistic regression is to calculate the predicted likelihood or probability of belonging to a class label or the other, right? So that's how logistic regression becomes popular. It can kind of imitate the likelihood and gives the statisticians or the econometricians very good estimate, very intuitive tools. With the probability, you can define another version that you can quantify the loss, which is the cross entropy. It basically calculates the log likelihood of the data given the current weights, right? So sum of squared error or log likelihood function, both of them describe the loss, although they describe different sides of the story. With sum of squared, it's not taking the log, but log likelihood, it takes the log. So the value is different. The sort of the curve may not be exactly the same, but in describing the learning curve, it's the same effect, right? And cross entropy is popular also because of the other fields that's related here that uses logistic regression, statisticians or econometricians, economic people. They like to use probabilities and they like to use cross entropy to describe how the model fits the data. They don't use sum of squared too much in logistic regression. So that's the only difference.
And the last doubt is, so why are we using only the net input function and activation function for measuring our accuracy? I mean, are they both enough to see
classification?
Yeah.
Okay. So let's see. So the question is really, why do I not calculate the error? Is that the question? Why do I stop at activation? Is that the question?
Yeah, I mean, when you're trying to find accuracy of our data set,
right.
We're just stopping at activation.
Mm-hmm.
I mean, so does that mean that activation function gives you the exact value of y? Or activation function?
I see. I think, let me explain it this way. The process inside the loop, if you try to summarize what's going on, there are several steps: net input, activation, gradient, weight update, and then update the weight, then calculate the cost. Right? All of these can be put into two bags. One is forward loop, the other is backward loop, or forward prop and back prop. Right. So net input and activation belongs to forward prop, and calculating error and then calculate gradient descent and weight update, they are back prop. The purpose of forward prop is really to make a decision. So this decision is kind of similar to the classification purpose, right? When you're making a classification, what you really are trying to do is to make a decision. You try to decide for a particular example, what should be the prediction, right? So you stop right before starting the back prop, and beginning with calculating the error, that's a back prop. So let's take a look at the forward prop. Now here, this is similar to logistic regression, Adeline logistic regression. It's don't simply change of the activation. So what does activation do? Activation is trying to transform the purely linear net input into something that's non-linear, right? With sigmoid activation, it compresses the real value space into between 0 and 1.
Yes.
So it tries to imitate the likelihood of predicting label 1, right? So given a net input Z, after activation, you get a number of 0.8. So that's the activation. This activation is it sort of imitates the likelihood of a class label, predicting class label 1. So this is as close as you can be in terms of making classification. That's why we stopped there.
Understood. And everything related to backpropping is basically optimizing a weight form.
Yeah.
Got it.
Yeah. Good.
Good, sir. Good.
You like this course?
I'm loving it, sir.
I can see that. I can see that. You're excited. Yeah.
But I was always wondering. So when I look at the data in the real world, how do I know which model to use for which kind of data set?
That's a very good question. And I can't emphasize more that in business problems and also in things that are related to business, not really, sort of medical or healthcare analytics, it's somewhat like business, but not really. It's definitely not like image classification. So let's put it this way. For a real world data set, how do you know which model to use? In computing space, I think the boundary is quite clear. When you try to use the machine, train the machine to perform something that relies on the vision, you definitely use neural network, computer vision types of models, and there are different types of deep learning models. You can go deeper. You can analyze the videos by using the frames, right, of the pictures. So those are computing, and those are not very similar to business problems. For business problems, it's kind of hard to know exactly because this field is also, it's growing. It's in infancy. You kind of, to apply machine learning models, you kind of have to apply a bunch of them and try to compare, try to establish a benchmark. Classic models include k-nearest neighbor, decision trees, random forest, and shallow neural network, or even regression or logistic regression give you a baseline. Once you have the baseline, then you begin the long process of trying to understand what's going on. It's very problem driven. You can't say too much about that, and it's painful inside the process. You can't see where is the end of it until sometimes. And the real problem is that you don't know about the ground truth. So and here's why. In image classification for a human, you can do a very well job. You can do 99.9% accuracy because we can differentiate a cat from a dog. If humans can do well, machine typically can find a solution that do as well as humans, or maybe even better. But in trying to predict default behavior, how the hell you can be sure for a human expert? Even for financial analysts, they can't be sure whether or not this customer will default. They have some indicators. They can build a regression model. That's basically what they can do. So their accuracy may be slightly better than 50%. So other than a random call, they can do 60% accuracy. They still make 4 mistakes every 10 customers. How can you expect the machine to be much better? So you don't see that line of the ultimate best performance. You don't even know where's the potential for machines. Then you try a bunch of things, start to lose hope because some of the models don't do much better than the basic models. So this is the space where we have a lot of questions. So it requires a lot of efforts and brave brave people to getting and trying to solve the problem. Yeah.
Thanks a lot.
Makes sense?
Yes, it totally makes sense.
Okay, great.
Yeah.
I'm glad you enjoy it. Well,
Thank you, sir.
well, let me know if you have more questions.
Sure, sir.
Okay.
Thanks so
Good
much.
night.
Have a good night.
Yeah, you too. Okay.